Imagine a planet where the average surface temperature is minus 50 degrees Celsius, where the ocean is covered with ice a kilometer thick from the equator to the poles, where the atmosphere is so dry that snow barely falls because there is almost nothing left to evaporate. Silence. Whiteness. The planet looks dead. This is not another world. This is Earth, 700 million years ago, and it happened more than once. Geologists call these episodes Snowball Earth, and it was precisely these events, not warmings but glaciations, that became the primary engine of evolutionary complexity on this planet. Because every time Earth froze and thawed, life made an evolutionary leap that could never have happened in comfortable warmth. Today we examine the full story, from the first global glaciation to the last glacial maximum that ended in geological terms just yesterday. Before we go any further, please subscribe to this channel. Your support really helps us to continue this work. Thank you. There is a number that reframes everything you think you know about the planet you live on. The number is 80. As in 80%. That is the approximate fraction of the past 2.5 million years, during which Earth has been in a glacial state, colder, drier, and more hostile than the world you were born into. The warm interglacial period in which all of recorded human history has occurred, in which agriculture was invented, in which every city ever built was built, in which every civilization rose and fell and left its ruins. This period is not the normal condition of the planet. It is an interruption. A pause between ice ages, 12,000 years long, that began when the last glacial maximum ended, and the ice sheets retreated, and the sea levels rose, and something like the world we recognize slowly assembled itself out of the wreckage of the cold. This fact, that the climate of modern civilization is an anomaly in the context of the planet's recent geological history, is the essential context for everything we are about to discuss. Because to understand why Earth freezes and what happens to life when it does, you first have to abandon the intuition that warmth is the default and cold is the aberration. In the geological record of the past several million years, it is precisely the other way around. The warm periods are brief, relatively rare, and, as the orbital mechanics that drive glacial cycles will show us, they end on a schedule that has nothing to do with what is convenient for the organisms that have adapted to them. But before we reach the ice ages of the Pleistocene, the ones that shaped our species and our landscape, and that left their fingerprints on every valley and lake and erratic boulder in the temperate world, we need to go much further back. Because the ice ages of the past 2.5 million years are not the only time Earth has frozen. They are not even the most dramatic time Earth has frozen. That distinction belongs to a set of events so extreme, so total, and so geologically consequential that they constitute one of the most important chapters in the entire history of life on this planet. Events that froze the ocean from pole to equator, that reduced life to its most minimal possible expression, and that, when they ended, triggered the most explosive radiation of biological complexity in the history of multicellular life. Geologists call these events Snowball Earth, and the story of how they happened and how life survived them And what emerged when they were over is the story we begin with. Because you cannot understand why the planet freezes without understanding the most extreme freezing it has ever done. And you cannot understand why life is the way it is without understanding what the ice did to it. The Cryogenian period, which spans from approximately 720 million to 635 million years ago, is named with geological precision for exactly what it was: a time of cold so profound and so total that it exceeds anything in the subsequent history of the planet. The name comes from the Greek for cold and birth, Cryos and Genesis, because the extreme cold of this period is understood to have been, paradoxically, one of the most generative events in the history of life. But we are getting ahead of ourselves. Before the birth, there was the cold. The evidence for Snowball Earth conditions comes from multiple independent lines of geological inquiry. And it is worth spending a moment on that evidence because it is genuinely extraordinary. The most dramatic piece comes from paleomagnetism. When rocks crystallize from molten material or sediment, magnetic minerals within them align themselves with Earth's magnetic field at the time of their formation, preserving a record of both the direction and inclination of the field. The inclination of the field is what matters here. Magnetic minerals align nearly parallel to the ground at the equator, where the field is horizontal, and nearly perpendicular to the ground at the poles, where the field points straight down. By analyzing the magnetic inclination of ancient rocks, geologists can determine the paleolatitude at which those rocks formed, where on Earth they were when they crystallized. The glacial deposits of the Cryogenian period, the tillites, the diamictites, the dropstone-bearing sediments that are the signatures of glacial activity, show paleomagnetic signatures consistent with equatorial latitudes. Not near equatorial, equatorial. Ice ages leave their distinctive sedimentary record at latitudes that, 700 million years ago, were at or near the equator. This means glaciers were present and active within a few degrees of the equatorial line, in a region that today experiences permanent summer heat and where no modern glacier has ever existed. The only way to get glaciers at equatorial latitudes is to get ice all the way to the equator, which means getting ice everywhere, which means a frozen planet. The paleomagnetic evidence is unambiguous on this point, and it has been replicated across multiple continental landmasses from multiple Cryogenian glacial horizons. The second major line of evidence comes from the carbon isotopic record. Carbon in the geological archive comes in two stable isotopes, carbon-12 and carbon-13, and their ratio in marine carbonates reflects the balance between biological productivity and the burial of organic carbon in the ocean. Living things preferentially incorporate carbon-12, so when marine productivity is high and organic carbon is being buried at high rates, the remaining dissolved inorganic carbon in the ocean becomes enriched in carbon-13, producing high isotopic values in the carbonates that precipitate from that water. When productivity collapses, as it would if the ocean's surface were frozen and photosynthesis were blocked, the isotopic ratio swings toward lower values, sometimes dramatically. The Cryogenian record shows some of the most extreme carbon isotope excursions in the entire geological archive. Massive negative swings that indicate near-total collapse of marine biological productivity, consistent with a frozen ocean surface blocking photosynthesis across most of the globe. These excursions are followed, at the end of each Snowball Earth episode, by equally dramatic positive swings as productivity recovered and organic carbon burial resumed. The carbon isotope record of the Cryogenian reads like a heartbeat, two pulses separated by a period of near flatline, the biological signature of a planet that nearly stopped producing life and then restarted. There were at least two major Snowball Earth events within the Cryogenian, separated by a brief warm interval. The older is called the Sturtian Glaciation, beginning approximately 717 million years ago and lasting an extraordinary 50 million years or more. The younger is the Marinoan Glaciation, beginning approximately 650 million years ago and lasting perhaps 15 million years. Both events are documented on multiple continents, in rocks that have been transported from their original positions by plate tectonics, but that retain the paleomagnetic record of their tropical origin. Both events show the characteristic carbon isotope signatures of biological collapse and recovery. Together, they represent somewhere between 65 and 75 million years of essentially continuous glacial conditions at a planetary scale, an interval of cold that makes the 2.5 million year Pleistocene glacial era look like a brief cold snap. The obvious question, the question that any geologist confronting this evidence immediately asks, is how? How does a planet freeze to its equator? What combination of circumstances drives the climate system to such an extreme state? And perhaps more urgently, once you get there, how do you get out? The mechanism that drives Snowball Earth onset is a runaway version of a feedback that operates in every glacial cycle, but that normally stabilizes before it runs to completion. The feedback is ice albedo. Ice and snow reflect more incoming solar radiation than open ocean or bare rock. So as ice expands, more solar energy is reflected back to space. The planet cools further and more ice forms. In normal glacial cycles, this feedback is limited by other processes. Changes in atmospheric greenhouse gas concentrations, shifts in ocean circulation, the orbital variations that alter the seasonal and latitudinal distribution of incoming sunlight. These stabilizing processes arrest the ice advance before it reaches the tropics. But 700 million years ago, the configuration of continents was different from today. The supercontinent Rodinia, which had assembled over the preceding hundreds of millions of years, was in the process of fragmenting, and many of the continental pieces that resulted from that fragmentation were distributed in the tropics. This matters because tropical landmasses, unlike tropical oceans, have very high albedo when covered with ice and snow. They reflect much more solar radiation than the dark tropical ocean would. The presence of large continental areas in the tropics during the Cryogenian may have tipped the ice albedo feedback from a self-limiting process into a runaway. Once ice advanced far enough into the tropics to cover significant continental area, the additional reflectivity may have pushed the system past the point at which any available stabilizing mechanism could arrest the advance, and the ice spread to the equator. The Sun itself is also part of the story. The Sun was approximately 6% less luminous during the Cryogenian than it is today, a consequence of stellar physics that predicts a gradual brightening of the Sun over its lifetime. A 6% reduction in solar luminosity may not sound significant, but in the context of the Earth's energy balance, it is the difference between a planet that can sustain equatorial temperatures above zero and one that cannot. The combination of a fainter Sun, high albedo tropical continents, and a carbon cycle that may have been drawing atmospheric CO2 to relatively low levels created the conditions for the ice albedo runaway to proceed further than it had in any subsequent glacial cycle. Once initiated, the snowball state is extraordinarily stable. The ice-covered ocean reflects most incoming sunlight, keeping temperatures cold enough to maintain the ice even in the tropics. The water cycle effectively shuts down. Evaporation is minimal over an ice-covered ocean. Precipitation is nearly absent, and the processes that normally cycle water and the chemical elements it carries through the climate system slow to near zero. Without liquid water to react with atmospheric CO2 through silicate weathering, the process by which carbon dioxide dissolves in rainwater reacts with silicate rocks and eventually ends up as carbonate minerals on the ocean floor, removing CO2 from the atmosphere. The carbon dioxide released by volcanic activity begins to accumulate, slowly, over millions of years. Because volcanoes do not stop erupting just because the planet is frozen. This is the escape mechanism. Volcanic outgassing of CO2 operates on geological timescales regardless of surface conditions because it is driven by the heat of Earth's interior rather than by surface processes. Over the 50 million years of the Sturgeon glaciation and the 15 million years of the Marinoan, volcanic CO2 accumulated in the atmosphere to concentrations that modern instruments would find almost unrecognizable. Estimates range from several hundred to several thousand times pre-industrial levels, compared to the 350 to 400 parts per million of the pre-industrial Holocene, and the 420-odd parts per million of today. At some threshold concentration, when enough heat was being trapped by the accumulated CO2 to overcome the reflectivity of the equatorial ice, the glaciation collapsed. Not gradually, rapidly. Once the ice began retreating from the tropics, the ice albedo feedback that had maintained the snowball ran in reverse, amplifying the warming as rapidly as it had amplified the cooling. The deglaciation of a snowball Earth event was, by all modeling evidence, extraordinarily fast, perhaps a few thousand years, to transition from global ice cover to a world where liquid water was present at all latitudes. And then, something happened that represents one of the more counterintuitive chapters in the history of life. The immediate aftermath of Snowball Earth deglaciation was not a world of recovery and gentle warming. It was a world of extraordinary chemical extremity. The accumulated CO2 that had melted the ice did not disappear when the ice melted. It remained in the atmosphere, driving global average temperatures to perhaps 40 to 50 degrees Celsius in the equatorial regions, creating a brief super greenhouse world of intense heat and chemical activity. Rivers of meltwater poured off the deglaciated continents, carrying enormous quantities of dissolved minerals into an ocean that had been largely cut off from the continental chemical weathering cycle for tens of millions of years. The ocean chemistry in the immediate aftermath of Snowball Earth was extraordinary, rich in dissolved minerals, subject to intense chemical reactions, and bathed in ultraviolet radiation that had previously been blocked by ice and snow. But before we examine what came after the snowball, we need to linger on what came through it. Because the question of how life survived a frozen planet is not an abstraction. It is a question about specific organisms in specific places, surviving through specific mechanisms. And the answers that the geological and biological evidence provides are as extraordinary as the catastrophe itself. The first and most important thing to understand about life during Snowball Earth is that it was not uniformly distributed across the planet before the glaciation began. 700 million years ago, the dominant forms of life were microbial, bacteria and archaea, single-celled eukaryotes, simple multicellular algae, and the stromatolite-building communities of cyanobacteria that had been the dominant biological ecosystem engineers for more than 2 billion years. These organisms were already adapted to a wide range of environmental extremes, and their metabolic diversity, the variety of chemical reactions they could use to extract energy from their environments, was far greater than that of any modern ecosystem dominated by complex multicellular life. This metabolic diversity was the key to survival. The deep ocean floor was almost certainly the most important refugium during Snowball Earth. Hydrothermal vent systems, the seafloor hot springs driven by volcanic heat from below, create environments that are entirely independent of sunlight and therefore entirely independent of the surface ocean. The organisms that inhabit modern hydrothermal vents derive their energy not from photosynthesis, but from chemolithotrophy, the oxidation of reduced inorganic compounds like hydrogen sulfide, methane, and iron that emerge from the vents. These chemolithotrophic communities are the most primitive on Earth in terms of their metabolic pathways and their independence from the surface biosphere. During Snowball Earth, when a kilometer of ice blocked sunlight from reaching the ocean's surface and essentially shut down photosynthesis across most of the globe, the hydrothermal vent communities continued operating exactly as they always had. The ice above was irrelevant to them. They drew their energy from the heat of the planet's interior, not from the light of the sun. We can be confident that hydrothermal vent communities persisted through Snowball Earth because the geological record shows no interruption in the types of mineral deposits associated with vent activity, and because the molecular clock analyses of the organisms that currently inhabit vents consistently place their deepest evolutionary divergences well before the Cryogenian. The vent communities are ancient. They predate the Snowball Earth events, and they survived them, and they are still there today, in essentially the same metabolic configuration, at the same geological settings, extracting the same chemical energy from the same volcanic systems that sustained them 700 million years ago. But the deep ocean vent communities were not the only refugia. The ice itself, paradoxically, may have provided habitable niches for certain specialized organisms. Modern polar ice is not a sterile solid. It is a complex physical environment containing liquid water channels, brine pockets, and surface melt pools that host diverse communities of cold-adapted microorganisms called psychrophiles. Antarctic sea ice, which reaches thicknesses of several meters in winter, supports algal communities that grow on the underside of the ice, deriving energy from the dim light that penetrates through the ice from above. Ice cores from Antarctica contain viable bacteria that have survived entombed in ice for hundreds of thousands of years. The organisms that occupy these extreme cold environments have developed specific molecular adaptations: antifreeze proteins, cold-active enzymes, membrane lipids that remain fluid at near freezing temperatures, that allow them to function under conditions that would kill most microorganisms. During Snowball Earth, similar ice-associated communities almost certainly existed, particularly at the equatorial regions where the ice was thinnest and where liquid water may have been periodically available at the surface during summer warming events. Some climate models suggest that even at the peak of Snowball Earth conditions, the equatorial ice may have been thin enough, perhaps a few tens of meters rather than the kilometer-scale thickness that characterized the polar regions, to allow occasional surface melting and the persistence of small liquid water environments in which photosynthetic organisms could survive, albeit under extraordinarily harsh conditions. The evidence for the continuity of photosynthetic life through Snowball Earth is preserved in the carbon isotope record. As we discussed earlier, the carbon isotope excursions of the Cryogenian indicate dramatic reductions in biological productivity during the glacial episodes, but they do not go to the extreme values that would be expected if photosynthesis had ceased entirely. A complete cessation of photosynthesis would have left a distinctive geochemical signature that is not observed. The inference is that photosynthetic communities were reduced to very low levels during the Snowball episodes, but were not entirely eliminated. They persisted in refugia, probably in the equatorial thin ice regions, and in coastal environments where geothermal heat from submarine volcanoes maintained patches of liquid water. The organisms that made it through were not, in general, the dominant life forms of the pre-Snowball world. The stromatolite-building cyanobacterial communities that had been the dominant visible life forms for 2 billion years were severely reduced. The more complex single-celled eukaryotes that had been diversifying in the Proterozoic oceans were pushed back. What persisted was the metabolically most versatile, physiologically most extreme-tolerant fraction of the pre-Snowball biosphere. The organisms that could subsist on the minimum possible energy input, that could survive in the most hostile physical environments, and that could exploit chemical energy sources independent of photosynthesis. These were not the dominant organisms of the pre-Snowball world, but they were the organisms that would inherit the post-Snowball world. Modern analogues help us understand what these refugial communities might have looked like. Lake Vostok in Antarctica, the liquid lake that exists 4 kilometers below the surface of the Antarctic ice sheet, maintained in liquid form by geothermal heat despite the crushing weight of ice above it, has been found to contain a surprisingly diverse microbial community, including bacteria, fungi, and even some multicellular organisms. Lake Vostok has been isolated from the surface world for somewhere between 15 and 25 million years, since the Antarctic ice sheet formed above it. Its biota represents what survives in liquid water environments completely isolated from sunlight and surface processes by a kilometer-scale ice barrier. This is perhaps the closest modern analogue to the conditions in which life persisted during Snowball Earth, and the fact that Lake Vostok is not sterile, that it contains a functioning, if simplified, ecosystem, is direct evidence that liquid water environments isolated by ice can sustain life for extended periods. Don Juan Pond in Antarctica provides another analogue, a hypersaline pool that remains liquid at temperatures far below the normal freezing point of water, maintained by the antifreeze properties of its extraordinary salt concentration. Don Juan Pond hosts microbial communities that survive in conditions that would be lethal to virtually any other known organism. The lesson from these modern extreme environments is consistent. Wherever liquid water exists on Earth, life finds a way to persist. And during Snowball Earth, liquid water existed in volcanic systems, in subglacial lakes, in thin equatorial ice environments, in coastal geothermal settings. Life was compressed, simplified, reduced to its most primitive and most versatile forms. But it was not extinguished. And then the ice retreated. The atmosphere flooded with volcanic CO2. The ocean opened, and the survivors faced an empty world. Not a world without resources. The post-Snowball ocean was extraordinarily rich in dissolved minerals after tens of millions of years of volcanic input without biological uptake. But a world without competitors. A world where the ecological niches that had been occupied before the snowball were now largely vacant, available to whatever organisms had the physiological capacity to exploit them. It was the largest and most sudden ecological opportunity in the history of complex life to that point. And life, as it always does when opportunity presents itself with this totality, took it. This post-snowball chemical environment was stressful and extreme. It was also, apparently, precisely the kind of environmental pressure that drives evolutionary innovation. The interval immediately following the Marinoan glaciation, the period from approximately 635 to 540 million years ago, called the Ediacaran, saw the first appearance in the fossil record of complex multicellular organisms. Not just simple colonial bacteria and single-celled eukaryotes, which had been present since long before the snowball events, but genuinely complex multicellular forms with differentiated tissues, organized body plans, and the morphological complexity that distinguishes animals from colonial microorganisms. The Ediacaran fauna, the strange, quilted, disc-shaped organisms that give the period its characteristic paleontological character, represent the first recognizable precursors to the animal body plans that would explode in diversity in the subsequent Cambrian period. The connection between the Snowball Earth events and the Ediacaran Cambrian diversification of complex life is not fully understood, and the scientific debate about the precise mechanisms is ongoing. But the temporal correlation is striking. Two of the most severe environmental events in the history of complex life, the Sturtian and Marinoan glaciations, are immediately followed by the two most significant radiations of biological complexity in the pre-Cambrian record. The Ediacaran fauna appear after the Marinoan and the Cambrian explosion, the astonishingly rapid diversification of animal body plans that occurred approximately 540 million years ago follows the end of the Ediacaran. There is a case to be made, and many researchers do make it, that the extreme environmental stress of the Snowball Earth events created the selection pressure that drove the evolution of the physiological and developmental complexity that eventually produced the animal kingdom. The logic is evolutionary. Extreme environments kill most organisms, but spare the ones with novel physiological or behavioral capacities that allow them to exploit refugia unavailable to their competitors. The survivors of each Snowball Earth episode were the organisms that could tolerate or exploit the extreme conditions of the frozen planet. The deep-sea hydrothermal vent communities, the subglacial meltwater environments, the liquid water pockets that may have persisted in tropical regions, the beneath-ice chemosynthetic ecosystems. These survivors carried the genetic and physiological innovations that had allowed them to persist. And when the climate recovered and ecological space opened up again, they radiated into that space, carrying those innovations with them. The Snowball Earth events were, in the language of evolutionary biology, severe bottlenecks followed by adaptive radiations, the same pattern operating at a planetary scale that produces evolutionary novelty at every level of the biological hierarchy. The Ediacaran organisms that appear in the fossil record after the Marinoan glaciation are among the most enigmatic creatures that have ever lived. They are not easy to interpret. They do not fit neatly into the categories of modern biology. And the debate about what they actually were, how they lived, how they fed, how they are related to the animal groups that succeeded them, is one of the oldest unresolved questions in paleobiology. But their very strangeness is part of what makes them important. Because the Ediacaran biota represents the first experiment in complex multicellular body plans, an experiment run in the empty post-snowball world, and its results shaped every animal that has lived since. The Ediacaran fossils are preserved primarily as impressions in fine-grained sediment, the external surfaces of soft-bodied organisms that sank to the seafloor and were rapidly buried in conditions that preserved their form before they could decay. They are found on every continent, in rocks spanning from approximately 635 to 541 million years ago, and they represent a fauna that in some respects looks alien to modern eyes. Dickinsonia, perhaps the most famous Ediacaran organism, is an oval, ribbed body that could reach more than a meter in length. It has no obvious mouth, no obvious gut, no obvious sensory organs, and no obvious bilateral symmetry in the strict sense. It has a central midline, but its internal structure is not organized in the way that most modern animals are organized. For decades, researchers debated whether Dickinsonia was an animal at all, or whether it was a fungus, a lichen, an alga, a colony of microorganisms, or something entirely without modern analogue. What some researchers called a vendobionts, a grade of organization that existed only in the Ediacaran and left no living descendants. The question was partially resolved by a remarkable discovery published in 2018, when Australian researchers analysing a Dickinsonia fossil found traces of cholesterol, a molecule produced exclusively by complex eukaryotes and particularly characteristic of animals, preserved in the fossil matrix. The cholesterol, still chemically detectable after 558 million years of burial, confirmed that Dickinsonia was a complex eukaryote, almost certainly an animal of some kind. But what kind of animal, and how it relates to the animal groups that appear in the subsequent Cambrian explosion, remains unclear. Dickinsonia has no obvious counterpart among modern animal phyla. It may represent an early branch of the animal tree that went extinct without leaving modern descendants, a failed experiment in animal body plans, tried in the Ediacaran and abandoned at the Cambrian boundary. Charnia and Charniodiscus, named for the Charnwood Forest in England where they were first discovered in the 1950s, represent another Ediacaran body plan. Frond-like organisms that were apparently anchored to the seafloor and extended upward into the water column. They resemble modern sea pens, which are colonial cnidarians related to corals and sea anemones, and they have been tentatively placed as early cnidarians or their relatives. But like Dickinsonia, their precise phylogenetic position is uncertain, and the resemblance to sea pens may be superficial, a result of convergent evolution toward the same functional form rather than of direct ancestry. Kimberella, from the White Sea region of Russia, is arguably the most convincingly animal-like of the Ediacaran organisms, and it has generated significant discussion because of what it implies about the timing of animal evolution. Kimberella is a bilaterally symmetrical organism. It has a distinct front and back, consistent with a directional mode of locomotion, with a tough outer covering and evidence of a soft underside. More strikingly, the fossil beds that preserve Kimberella also preserve what appear to be feeding traces, scratches, and rasping marks in the sediment around the organism that are consistent with the kind of feeding behavior seen in modern mollusks, which use a structure called a radula to scrape algae and organic material from surfaces. If Kimberella was indeed a mollusk-like organism, using a radula to feed, then complex bilaterian animals with a front-back body axis and complex feeding structures, were present by approximately 555 million years ago, tens of millions of years before the Cambrian explosion. Kimberella is particularly important because it suggests that the Cambrian explosion was not the sudden invention of complex animal organization from simple ancestors. Rather, the organizational complexity, the bilateral symmetry, the specialized tissues, the structured feeding apparatus, was already present in the Ediacaran, developed in the ecological space opened by the Snowball Earth events. What the Cambrian explosion represents, on this interpretation, is not the origin of complex animal organization, but the rapid diversification of hard parts, the shells, the mineralized skeletons, the external armors, that organisms evolved at the Ediacaran-Cambrian boundary in response to the appearance of predation as an ecological strategy. The appearance of eyes in the Cambrian, and simultaneously the appearance of hard defensive structures in prey organisms, suggests an evolutionary arms race. The sudden escalation of predator-prey interactions that drove the rapid diversification of hard part-bearing body plans. The disappearance of the Ediacaran fauna at the Cambrian boundary is as mysterious as their appearance. Some of the Ediacaran organisms simply disappear from the fossil record at the boundary. They are present below it and absent above it, with no clear descendants in the Cambrian fauna. Others appear to have given rise to Cambrian groups, but the connecting links are often obscure. The dominant hypothesis is that the Ediacaran organisms were largely outcompeted by the new Cambrian fauna, particularly by the burrowing animals that disturbed the microbial mat ecosystems on which many Ediacaran organisms depended, and by the predators that made soft-bodied, slow-moving organisms easy prey. The Cambrian world was a world of predation in a way that the Ediacaran world was not, and the organisms that had been successful in the peaceful Ediacaran seas were poorly equipped for the more competitive and dangerous Cambrian ocean. What the Ediacaran biota demonstrates, more broadly, is that complex multicellular organization evolved in the direct aftermath of the Snowball Earth events, in the ecological space those events created. The timing is not coincidental. The Sturtian and Marinoan glaciations, by nearly sterilizing the ocean and then releasing it into a world of extraordinary chemical richness and ecological openness, created the conditions for an evolutionary experiment that had never been possible before. And the experiment produced, over the 65 million years of the Ediacaran, the basic organizational toolkit: bilateral symmetry, tissue differentiation, directed locomotion, specialized feeding, that the Cambrian explosion would then multiply into the full diversity of the animal kingdom. The Cambrian explosion itself is one of the most dramatic events in the history of life. In approximately 20 million years, less than 5% of the time life has existed on Earth, virtually every major animal body plan that exists today appeared in the fossil record. The arthropods, with their jointed limbs and external skeletons, which today include insects, crustaceans, and spiders. The chordates, including the first vertebrates with their internal skeletons and spinal cords, our own distant ancestors. The mollusks, with their shells and radulas. The echinoderms, with their five-fold symmetry and internal calcite skeletons. The annelids, the brachiopods, the bryozoans, all of them appearing, diversifying, and establishing the ecological relationships of the predator-prey interactions that would characterize marine ecosystems for the next 500 million years, essentially to the present day. The Snowball Earth events did not directly cause the Cambrian explosion in any simple linear sense. The relationship is more subtle and more profound. The Snowball events reset the biological world, eliminated most of the incumbent organisms that had dominated the Proterozoic oceans, created an environment of extreme chemical richness in the post-glacial ocean, and opened ecological space for the experiments in complex multicellular organization that the Ediacaran biota represent. Those experiments produced the organizational toolkit that the Cambrian fauna then exploited and elaborated. Snowball Earth was the pressure that created the raw material. The Cambrian explosion was the expression of what that material could become. Now the timescale compresses from 700 million years to 2.5 million years ago, from the deep Cryogenian to the beginning of the Pleistocene. The planet went through warm and cool periods of various kinds, but nothing approaching the totality of the Snowball Earth events. Life diversified, colonized the land, developed the full repertoire of body plans and ecological strategies that characterize the modern biosphere. Then, approximately 2.5 million years ago, something changed. The planet entered a new mode of climate variability, not as extreme as the Snowball Earth events, but far more rhythmic, far more regular, and far more directly consequential for the evolutionary trajectory of a particular group of large-brained primates in Africa. The transition to the Pleistocene glacial cycles was not a sudden event, but a gradual intensification of a cooling trend that had been underway for much of the Cenozoic, the last 66 million years. The planet had been cooling since the early Eocene thermal maximum, approximately 52 million years ago, driven by the gradual drawdown of atmospheric CO2 through silicate weathering as the geology of the planet changed. The collision of India with Asia and the subsequent uplift of the Tibetan Plateau and Himalayas exposed enormous quantities of fresh silicate rock to the atmosphere, dramatically accelerating the weathering process that removes CO2. The separation of Antarctica from South America and Australia, which occurred between 35 and 30 million years ago, established the Antarctic circumpolar current and thermally isolated Antarctica, allowing the Antarctic ice sheet to grow to its current enormous size. Both events, the Himalayan uplift and the Antarctic isolation, contributed to the long Cenozoic cooling that eventually brought the planet to the threshold of Pleistocene glaciation. But the specific trigger for the rhythmic glacial-interglacial cycles of the past 2.5 million years came from an unexpected direction: the closing of the Central American Seaway. Before approximately 3 million years ago, a gap existed between North and South America that allowed ocean water to flow between the Atlantic and Pacific at low latitudes. This flow moderated the salinity difference between the two ocean basins and affected the strength of the Gulf Stream, the surface current that carries warm tropical water northeastward into the North Atlantic, and which is the visible expression of the Atlantic meridional overturning circulation that we discussed in our previous episode. When the Isthmus of Panama formed and closed the Central American Seaway approximately 3 million years ago, the Atlantic became saltier relative to the Pacific. The Gulf Stream strengthened, and the delivery of warm, moist air to the high latitudes of the Northern Hemisphere increased, paradoxically delivering more moisture to Greenland and northern Canada, which increased snowfall and contributed to the growth of the ice sheets that would characterize the Pleistocene. The rhythmic timing of the Pleistocene glacial cycles, however, is not primarily a consequence of plate tectonics. It is a consequence of astronomy. The orbital mechanics of the solar system impose regular, predictable variations on the amount of solar radiation reaching different latitudes of the Earth at different seasons, variations that operate on 3 distinct timescales: each associated with a different aspect of Earth's orbital geometry, and that were identified and quantified by the Serbian mathematician and geophysicist Milankovitch in a body of work that consumed much of the first half of the 20th century, and that has since been confirmed with a precision that Milankovitch himself probably could not have imagined. Milankovitch was born in 1879 in what is now Serbia, and he devoted the bulk of his scientific career to a problem that most of his contemporaries considered either intractable or irrelevant: the mathematical calculation of the solar radiation received at different latitudes of the Earth over hundreds of thousands of years, taking into account the cyclical variations in the shape of Earth's orbit, the orientation of its rotational axis, and the timing of the seasons relative to Earth's position in its orbit. His approach was purely mathematical. He was not a geologist or a paleoclimatologist, and the geological record that would eventually confirm his calculations was not available in the form it now takes. He was working out the orbital mechanics by calculation alone, using the laws of celestial mechanics to project the behavior of Earth's orbit millions of years into the past and future. The first orbital variation Milankovitch quantified is eccentricity, the degree to which Earth's orbit around the Sun deviates from a perfect circle. Earth's orbit is not a circle, but an ellipse, and the ellipticity of the orbit varies on a timescale of approximately 100,000 years, as gravitational interactions with the other planets, primarily Jupiter and Saturn, alternately stretch and compress the orbital path. When eccentricity is high, Earth's distance from the Sun varies significantly between its closest approach, called perihelion, and its farthest point, called aphelion, producing significant differences in the amount of solar energy received at different points in the year. When eccentricity is low, the orbit is nearly circular, and these seasonal variations in solar energy input are minimal. The second variation is axial tilt, or obliquity, the angle between Earth's rotational axis and the perpendicular to its orbital plane. Earth's axis is currently tilted at approximately 23.4 degrees, but this tilt varies between approximately 22 and 24.5 degrees on a timescale of approximately 41,000 years. When the axial tilt is greater, the seasonal contrast is more extreme. Summers are hotter and winters are colder at high latitudes, and vice versa. From the perspective of glacial cycles, changes in obliquity are particularly important for the high latitudes of the Northern Hemisphere, where the major Pleistocene ice sheets were located. Higher obliquity means hotter Northern Hemisphere summers, which promotes ice sheet melting. Lower obliquity means cooler Northern Hemisphere summers, which promotes ice sheet growth. The third variation is precession, the slow wobble of Earth's rotational axis, like the wobble of a spinning top, which cycles over approximately 26,000 years. Precession determines the timing of the seasons relative to Earth's position in its orbit. Where the Northern Hemisphere, summer occurs when Earth is near the Sun or far from the Sun. Currently, Northern Hemisphere summer occurs near aphelion, when Earth is at its maximum distance from the Sun, which moderates summer temperatures in the Northern Hemisphere. But approximately 13,000 years ago, half a precession cycle. Northern Hemisphere summer occurred near perihelion, when Earth was closest to the Sun, which made Northern Hemisphere summers hotter and more effective at melting ice. The precession cycle has a significant effect on the amplitude of the seasonal cycle and therefore on the growth and decay of ice sheets. Milankovitch's contribution was to calculate how these three orbital variations combine over geological time to modulate the amount of solar radiation received at the critical latitude of 65 degrees north, roughly the latitude of central Greenland and southern Alaska, during the Northern Hemisphere summer. Summer insolation at this latitude is what matters for glacial cycles, because the Northern Hemisphere ice sheets grow or shrink depending on whether summer is warm enough to melt the previous winter's snow accumulation. If summer insolation at 65 degrees north is high, ice melts and glaciers retreat. If it is low, ice survives the summer and glaciers advance. Milankovitch computed the history of this insolation for the past 600,000 years and found that it oscillated on the timescales of the orbital variations, producing a quantitative prediction for when glacial and interglacial conditions should have prevailed. The confirmation of Milankovitch's predictions came decades after his death, when the development of deep-sea sediment coring and the isotopic analysis of foraminifera shells provided a continuous, high-resolution record of past ocean temperatures and ice volumes going back hundreds of thousands of years. The match between the Milankovitch insolation cycles and the climate record preserved in the sediment cores was striking. The major glacial-interglacial cycles of the past several 100,000 years corresponded closely to the periods and phases of the orbital variations. The Milankovitch theory of ice ages, once considered speculative, was confirmed as one of the most powerful predictive frameworks in all of paleoclimatology. But the confirmation revealed a puzzle that has occupied climate scientists ever since. The orbital forcing by itself is small. The direct radiative effect of the Milankovitch cycles, the change in solar radiation reaching the Earth's surface, is insufficient by itself to explain the amplitude of the glacial-interglacial temperature swings recorded in the Geological archive. The orbital signal is real, but the climate response is amplified far beyond what the orbital forcing alone could produce. The amplification must come from feedbacks, processes within the climate system that amplify a small orbital signal into a large climate change. The most important of these feedbacks, and the one most directly relevant to the current state of the climate system, involves atmospheric carbon dioxide. During glacial periods, atmospheric CO2 falls to approximately 180 parts per million, less than half of its pre-industrial holocene value. During interglacial periods, it rises to approximately 280 parts per million. This variation in greenhouse gas concentration amplifies the orbital forcing by adding or removing additional radiative forcing from the greenhouse effect. The CO2 changes are not the primary driver of glacial cycles. They are a feedback that amplifies the orbital forcing, but they are responsible for a significant fraction of the total glacial-interglacial temperature difference of approximately 5 to 7 degrees Celsius in global mean temperature. How does atmospheric CO2 fall during glacial periods? The primary mechanism is the biological pump of the ocean. During glacial periods with expanded sea ice and altered ocean circulation, The delivery of nutrients to the surface ocean changes in ways that affect biological productivity and the burial of organic carbon. Additionally, cold glacial ocean waters dissolve more CO2 than warm and interglacial waters, a simple physical effect of the temperature dependence of gas solubility, and changes in dust delivery to the ocean. Glacial periods are dustier than interglacials because lower sea levels expose more continental shelf to wind erosion, deliver iron to iron-limited regions of the Southern Ocean and North Pacific, fertilizing biological productivity and driving additional carbon burial. All of these mechanisms work together to draw atmospheric CO2 down during glacial periods, amplifying the cooling. The ice albedo feedback is the second major amplifier. As ice sheets expand, they reflect more incoming solar radiation, cooling the planet further and promoting more ice growth. As they melt during interglacials, the dark ocean and land surfaces that are exposed absorb more solar radiation, warming the planet and promoting further ice loss. The ice albedo feedback approximately doubles the temperature response to the orbital forcing, contributing significantly to the difference between glacial and interglacial climates. The third major amplifier is water vapor. Warm air holds more water vapor than cold air, and water vapor is itself a greenhouse gas. As the climate warms during interglacials, atmospheric water vapor increases, trapping more outgoing long-wave radiation and amplifying the warming. As the climate cools during glacials, atmospheric water vapor decreases, reducing the greenhouse effect and amplifying the cooling. The water vapor feedback is the strongest and fastest acting of the major climate feedbacks. And then there is the Atlantic Meridional Overturning Circulation, the AMOC, that we examined in our previous episode. The AMOC plays a role in glacial cycles that is both important and incompletely understood, but whose basic outlines are clear from the paleoclimate record. During glacial periods, AMOC was significantly weaker than during interglacials, reducing the northward transport of tropical heat and contributing to the cooling and drying of the North Atlantic region. During the most extreme glacial episodes, the Heinrich events we discussed in detail in the previous episode, AMOC disrupted almost entirely, producing the dramatic climate reorganizations documented in the ice core and sediment records. AMOC is not just a feature of the current climate system, it is a component of the glacial cycle machinery, oscillating in strength over millennia, in response to orbital and ice sheet forcing, and amplifying the orbital signal through its effects on Northern Hemisphere heat distribution. Together, these feedbacks, CO2, ice albedo, water vapor, and AMOC, transform a small orbital signal into the dramatic glacial-interglacial swings that define the Pleistocene. The orbital forcing is the pacemaker. The feedbacks are the amplifiers. And understanding both is essential to understanding not just the ice ages of the past, but the climate trajectory of the present, because those same feedbacks are the ones that are currently being perturbed by the rapid increase in atmospheric CO2. Now the story turns to the biological consequences of this 2.5 million year oscillation between ice and warmth. and specifically to the consequences for the lineage of large-brained bipedal primates, whose story is the one we know most intimately. Because the appearance of the genus Homo in the African fossil record approximately 2.5 million years ago is not coincidental with the onset of Pleistocene glacial cycling. It is connected to it. The same orbital and climatic changes that initiated the rhythmic glacial-interglacial oscillations of the Pleistocene also transformed the African environments in which early hominins were evolving, creating the selective pressures that drove the evolution of the cognitive and behavioral capacities that eventually produced anatomically modern humans. The connection between climate variability and hominin evolution is encapsulated in a hypothesis called the variability selection hypothesis, developed by the paleoanthropologist Richard Potts of the Smithsonian Institution. The hypothesis argues that what drove hominin cognitive evolution was not adaptation to any particular environment, not the savanna, not the forest, not the woodland, but adaptation to environmental variability itself. The Pleistocene climate oscillations transformed African environments repeatedly over hundreds of thousands of years, alternating between wetter and drier conditions, expanding and contracting lakes and forests, shifting the distribution of resources across the landscape on timescales of thousands of years. Hominins that could flexibly adjust their behavior and technology to exploit a wider range of environmental conditions, hominins that could generalize rather than specialize, had a significant survival advantage in this unstable world. The selection pressure was not for adaptation to a particular niche, but for the capacity to switch between niches rapidly and effectively. This hypothesis explains a feature of the hominin fossil record that is otherwise puzzling: the correlation between periods of increased climate variability in Africa and the appearance of new hominin species and new technological innovations. The intensification of East African climate variability, approximately 1.5 to 2 million years ago, correlates with the appearance of Homo erectus, the first hominin to expand out of Africa, and the first with a brain approaching the size of later members of the genus. The further intensification of climate variability approximately 800,000 years ago correlates with the appearance of archaic Homo sapiens and the Acheulean stone tool technology. The extreme climate variability of the last few 100,000 years correlates with the appearance of anatomically modern Homo sapiens and the Upper Paleolithic technological revolution. Each major threshold in hominin cognitive and technological evolution appears to be associated with an increase in the amplitude or frequency of African climate variability, consistent with the variability selection hypothesis. The Ice Ages did not just create the landscape of the modern world by carving its valleys and depositing its soils. They created us, the cognitive flexibility, the behavioral plasticity, the capacity for symbolic thought and long-range planning and complex social organization that distinguishes Homo sapiens from every other species that has ever lived. These capacities were forged in the crucible of Pleistocene climate variability. We are, in a very direct sense, the product of the Ice Ages. The instability that the orbital cycles imposed on African environments over 2.5 million years selected for exactly the cognitive architecture that allows a primate to navigate radical environmental change. And then, having created that architecture, the Ice Ages provided the circumstances in which it would be put to its most dramatic test. The world that existed 26,000 years ago, at the peak of the last glacial maximum, was as different from the current world as any world that Homo sapiens has inhabited. Sea levels stood approximately 120 meters lower than today, exposing vast areas of continental shelf that are now covered by shallow seas. The Sahul Shelf between Australia and New Guinea was dry land, making them a single continent. The Sunda Shelf of Southeast Asia was largely exposed. The Bering Land Bridge, Beringia, connected Siberia to Alaska across what is now the Bering Strait, providing the corridor through which the first humans entered the Americas. The continental geography of the last glacial maximum were meaningfully different from the current geography, and any reconstruction of how our ancestors lived during this period must account for a world whose coastlines and land connections were radically unlike the ones we navigate today. Over northern North America and much of northern Europe, ice sheets of staggering dimension dominated the landscape. The Laurentide ice sheet covering North America reached thicknesses of 3 kilometers over what are now the Great Lakes region. The ice extended as far south as present-day New York City, Cincinnati, and Seattle. The Fennoscandian ice sheet covered all of Scandinavia, northern Germany, Poland, and much of the British Isles under ice that in places exceeded 2 kilometers in thickness. Beneath these ice sheets, the bedrock was depressed by the enormous weight of the overlying ice, a depression that is still being reversed today in a process called isostatic rebound, which causes Scandinavia and northern Canada to rise measurably each year as the ice that compressed them finished melting 12,000 years ago. The environments outside the ice sheet margins were not simply cold versions of modern environments. They were different kinds of environments with no direct modern equivalent. The periglacial zones immediately south of the ice sheets were characterized by permanently frozen ground, permafrost, overlain by a thin active layer that thawed briefly in summer. The vegetation was tundra and mammoth steppe, a cold, dry, windswept grassland that covered enormous areas of northern Eurasia and North America, and that supported a fauna of large herbivores whose diversity and biomass density exceeded anything in the modern world outside of a few African wildlife reserves. This is the world of the megafauna, and it deserves its own chapter, because the animals of the last glacial maximum represent a biosphere that is genuinely different from anything alive today, and whose disappearance is one of the great losses in the history of life since the end of the Cretaceous. The mammoth steppe was not merely cold tundra with mammoths. It was a productive, diverse grassland ecosystem supporting a community of large herbivores that included woolly mammoths, woolly rhinoceroses, cave lions, cave hyenas, cave bears, giant deer with antler spans of 3.5 meters, steppe bison, wild horses, reindeer, saiga antelope, musk ox, and in Eurasia alone, perhaps dozens of other large mammal species for which we have fossil records. In North America, the fauna included mastodons, mammoths, ground sloths the size of elephants, giant beavers, short-faced bears 3 times the size of a grizzly, American lions, American cheetahs, American horses, and tapirs in landscapes that are now temperate forest or grassland. This megafauna was not an evolutionary accident. It was the product of millions of years of adaptation to the cold, dry, productive grassland ecosystems of the glacial world. Ecosystems that were maintained by the combination of cold temperatures, low precipitation, and the grazing pressure of the enormous herbivore communities that both consumed and managed the vegetation. The mammoth steppe was, in ecological terms, the Pleistocene equivalent of the African savanna, a highly productive, species-rich grassland biome supporting large populations of diverse large mammals. And like the African savanna, it was maintained by a combination of climate and biological feedbacks that made it extraordinarily stable over geological timescales. We have described the physical world of the last glacial maximum, the ice sheets, the lowered sea levels, the exposed continental shelves, the mammoth steppe, and its extraordinary megafauna. But we have not yet talked about the people. And the people matter, because the last glacial maximum is not only a geological episode or a paleontological curiosity. It is the defining environmental context of fully modern human behavior. The moment in our history when everything we recognize as distinctly human, from complex art to long-distance trade to elaborate burial ritual, was already present and functioning in a world incomparably more hostile than the one we now inhabit. The human populations of the last glacial maximum were few. Global population estimates for the period 26,000 to 19,000 years ago suggest somewhere between 1 and 10 million individuals, a number that would fit comfortably in a single modern megacity, spread across the habitable portions of Africa, Asia, Europe, and Australia, with the Americas still unpeopled. These populations were small, mobile, and organized into bands of perhaps 20 to 50 individuals that moved seasonally across landscapes in pursuit of game and plant resources. They carried no permanent infrastructure. Everything they needed had to be portable or constructible from available materials. And the materials available in the periglacial zones of Europe and Asia were extraordinarily limited by modern standards. No wood in the open mammoth steppe, no clay in the permafrost, no quarried stone beyond what was available at the surface. Their solution to the problem of shelter in a treeless landscape demonstrates a degree of engineering ingenuity that is striking even by modern standards. At sites across Ukraine, Russia, and the Czech Republic, archaeologists have excavated the remains of what are called mammoth bone houses, structures whose frameworks were built from the bones and tusks of mammoths. Arranged in roughly circular patterns up to 8 meters in diameter, and presumably covered with hides and turf to create insulated living spaces. At the site of Mammoth in Ukraine, dated to approximately 15,000 years ago, 4 structures have been excavated that together used the bones of approximately 149 individual mammoths. The bones were carefully selected: large flat scapulae for walls, long limb bones for vertical supports, skulls arranged in patterns that may have had both structural and symbolic functions, curved tusks used as arches over doorways. These are not accidental accumulations. They are deliberate architectural choices made by people who understood structural engineering in wood, in whatever environment they inhabited, and who transferred that understanding to the materials available in a world where wood was scarce. The same ingenuity applied to clothing. Survival in temperatures that regularly reached -30 to -40 degrees Celsius in the periglacial zones of Europe and Asia required clothing sophisticated enough to provide genuine insulation, not just animal skins thrown over the body, but tailored garments with multiple layers, sewn seams, and design features that minimized heat loss. The evidence for tailored clothing during the last glacial maximum comes from bone needles, eyed needles, fine enough to sew tight seams in thin hide, found at upper Paleolithic sites across Eurasia, some dated to 30,000 years ago or more. The human populations of the glacial maximum were, in terms of their textile technology, not fundamentally different from Arctic peoples of the historic era, who survived at comparable latitudes: the Inuit, the Yupik, the Nenets, using multi-layer tailored clothing made from animal skins. The hunting technology of the last glacial maximum was equally sophisticated. At Sungir, a site in Russia dated to approximately 28,000 years ago, archaeologists excavated the burials of a man and 2 adolescents, whose grave goods included thousands of carefully drilled ivory beads, carved mammoth ivory figurines, and, most remarkably, 2 complete spears made from straightened mammoth ivory, each more than 2 meters long. Straightening mammoth ivory requires heat treatment, precise knowledge of the material's properties, and sustained patient work over many hours. The Sungir spears are not weapons of necessity. They are weapons of craftsmanship, made by people who had mastered a demanding technology and who apparently valued its products highly enough to include them as grave offerings. The hunting itself, the actual taking of mammoth, was almost certainly a communal endeavor requiring coordination across multiple families or bands. Mammoths were large, dangerous, and thick-skinned. A single spear thrust from a single hunter could wound one, but probably not kill it. The evidence from kill sites suggests that mammoths were driven toward natural traps, ravines, boggy ground, river bends, where their mobility was restricted and coordinated attacks from multiple hunters could be effective. This kind of organized communal hunt requires advanced planning, communication of complex tactical information, and the coordination of action among individuals who may not all be related by immediate kinship. It is, in short, exactly the kind of cognitively demanding social behavior that the variability selection hypothesis predicts should have been selected for by the challenges of the Pleistocene environment. And then there is the art. The cave paintings of Europe, Lascaux, Chauvet, Altamira, Pechmerle, and dozens of other sites were made primarily during the last glacial maximum and the preceding glacial period, at a time when northwestern Europe was subject to subarctic conditions, and the artists who made them were people who survived by hunting mammoth and reindeer on a cold, windy steppe. Chauvet Cave in southern France, which contains some of the oldest and most technically accomplished cave paintings known, was decorated approximately 36,000 years ago, at a time when the glacial maximum was approaching, and the climate of Europe was deteriorating from what had been a relatively mild period. The painters of Chauvet had never experienced a warm interglacial. They were people of the ice, fully adapted to a world incomparably harsher than the one in which European civilization later developed, and they made images of extraordinary beauty and technical sophistication on the walls of caves that they apparently visited specifically to paint. The art is significant not only as evidence of aesthetic capacity, but as evidence of something more fundamental: the capacity for abstract symbolic thought. Cave paintings represent animals that are not physically present. They are mental images externalized onto a physical surface, the visible trace of a cognitive process that requires the ability to hold a mental model of an absent object and reproduce it in a different medium. This is a cognitive capacity that, as far as we know, is unique to Homo sapiens. And it was operating at full modern intensity during the last glacial maximum in people who were simultaneously solving the engineering problems of mammoth bone construction and the tactical problems of coordinated mammoth hunting. The people of the last glacial maximum were not primitive versions of us. They were us, anatomically, cognitively, and in terms of their social and symbolic capabilities, fully modern human beings, operating in an environment so hostile that survival required capabilities that most modern humans in industrial societies never need to deploy. Their lives were not comfortable. The evidence from skeletal material shows high levels of physical stress, frequent injury, significant nutritional stress during the worst winters, and life expectancies that, by modern standards, were short, but they were not cognitively limited. The brains they brought to the problem of survival in the glacial maximum were the same brains we bring to the problems of the 21st century. The difference was not capacity, it was context. The populations of eastern Siberia, who eventually crossed Beringia into the Americas, were the descendants of these glacial survivors, people whose lineages had been shaped by tens of thousands of years of adaptation to some of the harshest environments on Earth. When they crossed the land bridge into Alaska, they were moving into a world that, while cold, was not significantly more challenging than the Siberian environments their ancestors had inhabited. What was different about the Americas was its ecological novelty, an entire continent of megafauna that had never seen human hunters, animals that had no evolved fear of the two-legged predator that was about to arrive from the west. But the mammoth steppe was not destined to survive the end of the Ice Age. As the climate warmed after the last glacial maximum, driven by the same orbital forcings that had initiated the glaciation, now running in the opposite direction, the conditions that had maintained the mammoth steppe began to disappear. Temperatures rose, precipitation increased. The dry, cold grassland gave way to wetter, shrubby tundra and eventually to boreal forest across vast areas of northern Eurasia and North America. The vegetation change was catastrophic for the grazing megafauna. Woolly mammoths, woolly rhinoceroses, and the other cold-adapted specialists of the mammoth steppe were adapted to a world of dry, cold grassland, not to the wet, shrubby, forest-dominated environments that replaced it. Their habitat disappeared from under them, contracting to smaller and smaller refugia at the northern margins of the continents as the boreal forest advanced. But the climate change was not acting alone. At approximately the same time that the Mammoth steppe was collapsing under post-glacial warming, anatomically modern humans were expanding their geographic range across the globe, into Eurasia, across Beringia, into the Americas, and to the most remote islands of the Pacific. And the arrival of human hunters correlates at multiple geographic locations and on multiple continents, with rapid extinctions of the large mammal fauna. The pattern is stark. In Africa, where hominins and large mammals had been co-evolving for millions of years, and where the megafauna had time to adapt to the presence of skilled human hunters, megafaunal extinctions were relatively modest. In Eurasia, where Homo sapiens arrived more recently, the extinctions were more severe. In North America, where modern humans arrived only 15,000 years ago, and in Australia, where they arrived 50 to 60,000 years ago, the extinctions were catastrophic, eliminating the majority of the large mammal fauna within millennia of human arrival. The debate over the relative roles of climate and human hunting in the Pleistocene megafauna extinctions is one of the most contentious in quaternary science, and it has not been fully resolved. The evidence increasingly points toward a combination of both factors, operating synergistically. The climate change weakened the megafauna by destroying their habitat and reducing their populations to more vulnerable levels, while the arrival of skilled human hunters delivered the killing blow to populations that might otherwise have survived the habitat changes in refugia. The woolly mammoth, whose range contracted to the Siberian tundra and a few Arctic islands as the Holocene began, hung on in its island refugia for thousands of years after the mainland extinction, surviving on Wrangel Island in the Arctic Ocean until approximately 4,000 years ago, long after the Egyptian pyramids were built. The proximate cause of the Wrangel Island mammoth extinction was almost certainly human arrival on the island, not climate. The extinction of the Pleistocene megafauna is one of the great unsolved crimes in the history of life. Not unsolved in the sense that we have no suspects. We have two, and they are both compelling. It is unsolved in the deeper sense that the debate about their relative culpability has been conducted for decades at the highest levels of quaternary science, generating thousands of papers and several rounds of apparently definitive conclusions that were subsequently challenged by new data. What has emerged is a picture of considerable complexity, in which the answer varies by continent, by species, by the specific timing of human arrival and climate change at each location, and in which the most honest summary is that both suspects played significant roles, and that determining which was primary in any given case requires a level of temporal precision that the fossil record has only recently become capable of providing. The climate hypothesis for megafaunal extinction rests on the straightforward observation that the last glacial maximum terminated at approximately the same time as the major megafaunal extinctions, and that the transformation of the Mammoth steppe into tundra and boreal forest, as the climate warmed, would have been catastrophic for the cold-adapted grazing specialists that the steppe supported. The woolly mammoth, the woolly rhinoceros, the cave lion, the giant deer, all were adapted to a cold, dry, productive grassland environment that does not exist anywhere on Earth today. When that environment contracted and ultimately disappeared from most of its former range, The animals adapted to it would have had nowhere to go. Their habitat effectively ceased to exist, and with it, the possibility of their survival in viable numbers. The evidence for the climate hypothesis includes the timing of vegetation change, which in many regions of northern Eurasia clearly precedes or coincides with the megafaunal extinctions, and the observation that large mammal extinctions have occurred at other glacial terminations in the deeper Pleistocene without the involvement of human hunters. The megafauna of earlier interglacials did not all survive into the subsequent glacial period. Many species went extinct at previous glacial terminations, suggesting that the transition from glacial to interglacial conditions is inherently stressful for cold-adapted specialists regardless of whether humans are present. The human hunting hypothesis, sometimes called the overkill hypothesis, in the dramatic formulation proposed by the ecologist Paul Martin in the 1970s, rests on a different set of observations. The most powerful of these is the geographic pattern of extinction. In Africa, where hominins have been present for millions of years, and where the megafauna had millions of years to evolve, alongside increasingly sophisticated human hunters, the extinction rate at the end of the Pleistocene was relatively modest. A few species lost, but the majority of the large mammal fauna surviving. In Eurasia, where anatomically modern humans arrived perhaps 45,000 years ago, the extinctions were more severe, but still partial. In Australia, where modern humans arrived approximately 50 to 65,000 years ago, the megafaunal extinctions were devastating. Roughly 40 species of large mammals lost, including all native herbivores larger than about 100 kilograms, within a relatively short interval of human arrival. And in the Americas, where humans arrived approximately 15,000 years ago, the extinctions were catastrophic. 35 genera of large mammals lost, within perhaps 2,000 years of human colonization. The pattern is striking because the timing of extinction on each continent correlates with the timing of human arrival, not with the timing of the most severe climate change. Australia is the clearest case. The extinctions there occurred approximately 50,000 years ago, during a glacial period rather than at a glacial termination. In the absence of the dramatic habitat transformation that characterized the end of the last glacial maximum in the Northern Hemisphere, the Australian megafauna, diprotodons the size of hippopotamuses, giant kangaroos, marsupial lions, giant wombats, huge flightless birds, lived through multiple previous glaciations and terminations without significant extinction. The only novel event at the time of their disappearance was the arrival of anatomically modern humans from Southeast Asia. The case of the woolly mammoth provides perhaps the most compelling evidence for the human hunting hypothesis, because it offers a natural experiment in which the same species survived in two different settings with different human presence. On the Siberian mainland, woolly mammoths went extinct approximately 10,000 years ago, shortly after the Holocene began and human populations in Siberia became more numerous and more mobile. On Wrangel Island in the Arctic Ocean, isolated from the mainland by ocean that formed when sea levels rose at the end of the glaciation, a dwarf population of woolly mammoths survived until approximately 4,000 years ago, long after the mainland extinction, long after the climate had warmed, long after the vegetation had changed. The Wrangel Island mammoths survived precisely as long as the island remained uninhabited by humans. When humans arrived on Wrangel Island, the mammoths went extinct within a geologically brief interval. The simplest explanation for this pattern is that the absence of human hunters, not the presence of suitable habitat, is what allowed the Wrangel Island population to persist. New research published in 2024 and 2025 has added further detail to the picture. High-precision radiocarbon dating of megafaunal remains from multiple species across Eurasia and the Americas has allowed researchers to reconstruct the chronology of individual species extinctions with enough temporal resolution to test the climate and human hunting hypotheses against specific predictions. The results, taken together, support what is now called the synergy hypothesis. The idea that climate change and human hunting acted together, with each factor making the other more effective. Climate change reduced population sizes and habitat connectivity, making megafauna populations more vulnerable to the hunting pressure that human arrival brought. Human hunting reduced populations below the threshold at which they could recover from habitat loss. Neither factor alone was sufficient to drive the extinctions, but their combination, operating simultaneously on populations that were already under stress, was lethal. The research of Esker Villeslev's group, published in 2025, analyzed ancient environmental DNA from permafrost sediments across Siberia and the Arctic, reconstructing the vegetation history of the mammoth steppe at the same temporal resolution as the mammal fossil record. Their findings showed that the vegetation transformation, the loss of productive grassland and its replacement by less nutritious sedge tundra, began in most regions at approximately the same time as the first evidence of significant human presence, rather than being a straightforward consequence of warming. This suggests that the vegetation change itself may have been partly driven by the loss of the megafaunal grazers that maintained the mammoth steppe ecosystem through their grazing and trampling. A feedback in which human hunting of the grazers destabilized the ecosystem that the grazers had maintained, accelerating the vegetation transition that then further reduced the grazers' habitat. The crime was more complex than either suspect alone. It was a conspiracy. The loss of the megafauna is not only an ecological story. It is a cultural and cognitive story about what happens when a predator that evolved in one ecological context encounters prey that evolved in another. The megafauna of the Americas and Australia had spent millions of years evolving in the absence of large bipedal hunters using projectile weapons. They had no behavioral adaptations to the specific hunting strategies that Homo sapiens employed. They did not flee from human approach, did not associate the smell or sight of humans with danger, did not learn from observation of other individuals being hunted that this particular predator required avoidance. They were, in the language of conservation biology, naive prey, animals whose threat avoidance systems had never been calibrated to the specific danger that human hunters represented. The animals that had co-evolved with hominins in Africa over millions of years, the elephants, the lions, the buffalo, were not naive. They had learned over generations that humans were dangerous. The American mastodon and the Australian diprotodon had not. And they paid for that naivety with extinction. And then the younger dryas arrived as the last significant cold interruption before the full establishment of the Holocene. Approximately 12,900 years ago, as the planet was warming and the ice sheets retreating, AMOC disrupted, as we discussed in detail in our previous episode, and temperatures in the North Atlantic region plummeted by 10 to 15 degrees within a decade. The Younger Dryas lasted 1,200 years, long enough to re-expand glaciers that had been retreating, to reverse the northward advance of forests and the retreat of tundra, and to deliver a final extreme stress to the already pressured megafauna and the human populations that depended on them. Then AMOC recovered, the Holocene warmed, and the glacial world was finished. Finished, but not forgotten. The landscape of the post-glacial world bears the indelible mark of the ice that shaped it. The Great Lakes of North America are basins scoured by the Laurentide ice sheet. The fjords of Norway and New Zealand are valleys carved by glaciers and flooded by rising post-glacial seas. The loess, the fine-grained, wind-blown sediment deposited by glacial-era winds that covers vast areas of China, the American Midwest, and Central Europe, is one of the most fertile soil-parent materials on Earth. The glacial legacy on which a significant fraction of modern food production depends. The topography of northern Europe, from the moraines of northern Germany to the drumlins of Ireland, is a direct record of ice sheet dynamics and retreat. Even the Hudson River, which carved a submarine canyon on the continental shelf that now lies under more than 100 meters of ocean, is a relic of the glacial era, when the river flowed to a coastline far east of modern Manhattan. The Holocene that followed the glacial world has been, by Pleistocene standards, extraordinarily stable. The 12,000 years of the Holocene represent one of the longest continuous warm intervals in the past 800,000 years of the climate record, longer than most previous interglacials, and characterized by a degree of climate stability that has no close parallel in the Pleistocene record. This stability is what made the Neolithic agricultural revolution possible, what allowed the development of settled civilization, what created the conditions for the long-term accumulation of knowledge and technology that characterizes the past 10,000 years of human history. Every city, every written text, every scientific discovery, every technological achievement of human civilization has occurred within this anomalously stable warm pause in an otherwise glacially dominated climate system. And here is the question that the orbital mechanics of the solar system raises, and that every honest discussion of the current climate situation must eventually confront. When will the next ice age begin? The orbital variations that drive the glacial cycles are predictable. They are, after all, the product of the deterministic mechanics of the solar system, calculable centuries in advance. By the calculations of the Milankovitch cycles, the next period of low summer insolation at high northern hemisphere latitudes, the next orbital configuration favorable to ice sheet growth, should begin approximately 50,000 years from now, as the current orbital state progresses through its cycle. In the absence of other perturbations, The Holocene interglacial should eventually give way to a new glacial period, perhaps in 50,000 to 100,000 years. But there is now another variable in the equation. Atmospheric CO2 is currently at approximately 420 parts per million, higher than at any point in the past 3 to 5 million years, higher than at any interglacial peak in the ice core record, and rising at a rate with no geological precedent in the Pleistocene. The CO2 that has been added to the atmosphere by the combustion of fossil fuels and other industrial activities is a greenhouse gas forcing that operates on the same physical principles as the CO2 changes that amplify glacial cycles. But it is being applied in the opposite direction, and at a rate and magnitude that exceeds any natural CO2 change in the recent geological record. Research published in the past decade has examined what the current elevated CO2 will do to the orbital timing of the next glacial inception. The conclusion is remarkable. The anthropogenic CO2 already in the atmosphere and committed to the atmosphere by existing emissions trajectories is probably sufficient to delay or prevent the next glacial inception entirely. The orbital forcing that would normally be expected to drive ice sheet growth in the coming tens of thousands of years is insufficient to overcome the additional greenhouse warming that the elevated CO2 will maintain for geological timescales. CO2 persists in the atmosphere on timescales of thousands to tens of thousands of years once emitted, because the natural carbon cycle processes that remove it operate slowly. The human species, in the course of industrial activity spanning roughly 2 centuries, has altered the orbital pacing of ice ages that has governed the planet's climate for the past 2.5 million years. We have, in effect, cancelled the next ice age. This is the most extraordinary statement in this entire story, and it deserves to sit in your mind for a moment. The glacial cycles that shaped our species, that carved our landscapes, that drove the evolution of our cognitive architecture, and that structured the ecological world we inhabit, those cycles are now being disrupted by the very species they created. The mechanism that produced us is being altered by us. The planet that is fundamentally an ice planet, that has spent 80% of the past 2.5 million years colder than today, may be entering an interval of warmth with no Pleistocene precedent. Not because of orbital mechanics, but because of the chemistry of an atmosphere that one species has changed faster than the geological carbon cycle can correct. The orbital calculation that predicts the next glacial inception is not controversial. The Milankovitch cycles are deterministic. They are the product of the gravitational physics of the solar system, calculable with high precision using well-established mathematical methods. The current orbital configuration, specifically the combination of relatively low eccentricity and the current phase of the precession cycle, produces a level of summer insolation at 65 degrees north that is not dramatically below the modern average. The next significant reduction in Northern Hemisphere summer insolation, the next orbital configuration that would, in the absence of other factors, favor ice sheet growth, is approximately 50,000 years in the future. Without human modification of the climate system, the Holocene would likely continue for something in the range of 50,000 years, before the orbital forcing drove the planet toward the next glacial inception. But we have modified the climate system dramatically. And the question of what that modification means for the timing and character of the next ice age is one that geologists and climate scientists have been examining with increasing urgency as the scale of anthropogenic CO2 emissions has become clear. The key paper is one published in 2016 by Andrzej Ganopolski and colleagues at the Potsdam Institute for Climate Impact Research in the journal Nature. Ganopolski's group ran a series of climate simulations examining how different levels of atmospheric CO2 would affect the orbital threshold for glacial inception, the minimum northern hemisphere summer insolation at which an ice sheet could begin to grow. Their findings were unambiguous. At pre-industrial CO2 levels of approximately 280 parts per million, the orbital forcing of the next 50,000 years would be sufficient to initiate a new glacial period. But at CO2 levels above approximately 240 parts per million, a threshold that was crossed thousands of years ago, the additional greenhouse warming prevents the ice albedo feedback from reaching the level needed to sustain ice sheet growth, even when the orbital forcing is at its minimum. Current atmospheric CO2 stands at approximately 420 parts per million, more than 75% above the pre-industrial level, and more than 180% above the threshold that Ganopolski identified as necessary for glacial inception. Even if all anthropogenic CO2 emissions stopped immediately, the CO2 already in the atmosphere would persist for thousands to tens of thousands of years before the natural carbon cycle fully removed it. The geological record shows that after previous large releases of CO2, like the Paleocene-Eocene thermal maximum 56 million years ago, the carbon cycle took approximately 100,000 to 200,000 years to return atmospheric CO2 to pre-event levels. On that timescale, the next scheduled glacial inception at 50,000 years, and possibly the one after that, will occur with substantially elevated CO2 levels that will prevent the orbital forcing from initiating ice sheet growth. The most recent modeling work, published by Thomas et al. In 2024, refined the Ganopolski analysis by incorporating more realistic representations of ice sheet dynamics and carbon cycle feedbacks. Their conclusions were similar. Under any emissions scenario involving significant fossil fuel combustion, the next glacial inception is likely to be delayed by at least 100,000 years relative to the orbital prediction, and may be delayed by several 100,000 years if high emissions trajectories continue. We have, in the language of the geological record, added at least one and possibly several interglacial periods to the natural sequence, not by altering the orbital mechanics, which are beyond any human technological capacity, but by changing the atmospheric chemistry in a way that prevents the orbital forcing from driving ice sheet growth. 2 centuries against 2.5 million years. The numbers do not require commentary. They require only to be placed beside each other. The implications of cancelling the next ice age extend far beyond the obvious point that the world will remain warmer than it would otherwise be. They reach into ecology and evolution in ways that are not immediately obvious. Glacial cycles are not just climate events. They are ecological drivers of the first order. Every species in the temperate and subarctic zones of the planet has evolved in the context of the repeated advance and retreat of ice sheets, the cyclical expansion and contraction of habitats, the repeated isolation and reconnection of populations, the alternation between cold-adapted and warm-adapted communities. That has been the dominant pattern of ecological change for the past 2.5 million years. The glacial cycles created the modern distribution of species. They created the current geography of biodiversity. They drove the speciation events that produced the diversity we see in the temperate zone today. And they are now being switched off. The ecological consequences of removing the glacial cycle from the climate system are genuinely unknown, because nothing comparable has happened in the past 2.5 million years. The last time Earth experienced a prolonged warm period without glacial cycles was the Pliocene, the geological epoch preceding the Pleistocene, when the orbital configuration and CO2 levels were both somewhat different from today. The Pliocene world was warmer than today, with smaller ice sheets, higher sea levels, and a different distribution of vegetation zones. It was a functioning biosphere, as all previous biospheres have been functioning biospheres. But it was a different biosphere, not better or worse in any absolute sense, but different in its species composition, its ecological structure, and its geographic distribution of diversity. The organisms that are best adapted to the glacial-interglacial cycle, the species that speciated during glacial periods in isolated refugia and expanded during interglacials, the species whose population structures reflect the repeated demographic contractions and expansions of the Pleistocene, the species whose physiological tolerances are calibrated to the range of conditions that the glacial cycles produced. These species are now facing a climate trajectory that has no precedent in the history of their lineages. Some will adapt, some will migrate, some will go extinct. The balance among these outcomes for any particular species in any particular region is the subject of active conservation biology research. But the aggregate outcome, the reshaping of the biosphere's species composition and geographic distribution in response to a climate trajectory without glacial cycle precedent, is virtually certain on any honest reading of the ecological evidence. There is also the question of what cancelling the Ice Age means for the long-term trajectory of human civilization. The Holocene's 12,000 years of unusual climate stability enabled the development of agriculture, cities, and the accumulated knowledge base of civilization. The next Ice Age, whenever it would have occurred, would eventually have terminated the Holocene and returned the planet to glacial conditions that would have made the agriculture and settlement patterns of modern civilization unsustainable across large areas. In that narrow sense, the anthropogenic delay of the next glacial inception is a benefit to agricultural civilization. It extends the window of stable, warm climate in which the food production systems that feed 8 billion people can operate. But it extends that window at the cost of the climate stability that the Holocene represented, replacing the glacial risk with the risk of anthropogenic warming and trading one form of agricultural disruption for another. The geological record does not offer a precedent for this trade-off because it has never happened before. A biological species has never before altered the orbital pacing of glacial cycles. The experiment is novel, the outcome is uncertain, and the geological archive, for all its extraordinary value as a record of the past, cannot tell us how this particular experiment will end. Because the experiment is being run for the first time, faster than any previous comparable forcing, by an agent capable of understanding what it is doing, but not yet certain of what it should do. Now let me tell you what I think about all of this. As someone who has spent time with the geological record across all the timescales we have covered today, from the Cryogenian Snowball Earth to the Pleistocene glacial cycles to the holocene anomaly we currently inhabit, the thing that strikes me most forcefully about the full story of Earth's ice ages is not any single event or discovery. It is the pattern of how the planet responds to perturbations. Snowball Earth happened because a series of feedbacks, ice albedo, reduced solar luminosity, continental configuration, reinforced each other until the system reached a state no individual factor could have produced alone. The escape from Snowball Earth happened because a different feedback, volcanic CO2 accumulation, eventually overcame the stability of the frozen state and drove a rapid transition in the opposite direction. The Pleistocene glacial cycles happen because small orbital forcings are amplified by CO2, ice albedo, water vapor, and AMOC, feedbacks into large climate swings. The Younger Dryas happened because a single pulse of fresh water crossed a threshold. One pulse, 1 decade, 1,200 years of consequences. The pattern is one of a climate system with strong internal feedbacks, capable of amplifying small forcings into large responses, and with threshold behaviors that can produce abrupt transitions between different stable states. This is not a gradual, linear system that responds proportionally to every perturbation. It is a non-linear system with preferred states and the capacity for rapid reorganization when thresholds are crossed. Understanding this pattern, really understanding it in its full geological depth, changes how you read the current situation. When geologists say that atmospheric CO2 is at levels not seen in 3 to 5 million years, they are not citing a number. They are locating the current experiment in the context of a system with a known history of dramatic responses to forcings of this magnitude. When climate scientists project temperature increases of 2 to 4 degrees Celsius by the end of this century, they are projecting changes comparable in magnitude to the difference between a glacial maximum and an interglacial. The difference between a world with 3-kilometer ice sheets over New York and a world without them. These are not abstract numbers. They are geological magnitudes with geological precedents, and the geological precedents are in the archive if you know where to look. The second thing I think about is evolution. The ice ages made us. The cognitive flexibility, the problem-solving capacity, the ability to cooperate in large groups toward distant goals, the capacity for symbolic thought and cumulative culture. All of these were selected for by the climate variability of the Pleistocene. We are, literally, the product of the instability that the orbital cycles imposed on African environments for 2.5 million years. The question of what the stability, or the novel instability, of the coming millennia will do to the evolutionary trajectory of life on this planet is one that the geological record illuminates but cannot answer. Because the current experiment is being run faster than any previous natural forcing. The third thing, and this is the one that the Snowball Earth story makes most viscerally clear, is resilience. Life survived a frozen ocean covering the entire planet. It survived conditions that by any reasonable expectation should have been lethal for complex multicellular organisms. And not only did it survive, it emerged from those events more complex, more diverse, and more capable than it had been before. The biosphere is extraordinarily resilient on geological timescales. It has survived 5 mass extinctions, 2 global glaciations, multiple supervolcanic episodes, and asteroid impacts. It will survive whatever the current experiment produces. But survival is not the same as preservation. The organisms that survived Snowball Earth were not the organisms that had thrived before it. The biosphere that recovered was not the biosphere that had existed. The megafauna that survived the last ice age were not the same as the megafauna that preceded it. And the world that will exist on the other side of whatever transition the current human forcing produces, whether that is a few centuries of elevated temperature before the planet's carbon cycle corrects the perturbation, or a 1,000-year disruption of the oceanic circulation and monsoon systems, or something more severe. That world will be different from this one. Not dead, not lifeless, but different. Snowball Earth was the most dramatic episode in the history of life's relationship with cold. The Pleistocene glacial cycles were the most recent, and we, the species that those cycles created, the primate whose remarkable cognitive architecture was selected for by 2.5 million years of climate instability, are now the forcing. The planet has been here before, in various senses. It has been colder and it has been warmer. It has been frozen and it has been free. What it has not been in 4.5 billion years of geological history is subject to a forcing applied this rapidly by a biological agent capable of understanding what it is doing. That is the situation we are in. The geological record is the context. The ice ages are the precedent. And the question of what we do with the knowledge that the record provides is the most consequential question the species that the ice ages created has ever faced.